So hello, welcome to Me But Online. I apologize. Don't have control over it. I was told I had to teach online for the snow day, so you're getting this online. So some of you in the room, some of you watching this as a video afterwards. For those of you in the room, if you have any questions at any point, I kind of have screen set up a way that I can't really see you guys. Just unmute and interrupt me, and I will answer any questions. It's feel free to interrupt as needed. It's the best I can do. Um, Hopefully I have my audio set up correctly that you will hear when I play videos. If not, we'll find out. Because I just realized I forgot to double check that setting. So, today I am going to be starting chapter two. Um, Chapter two is on motion. This is going to be, yeah, a lot of things are just about things moving and how we're going to define motion, how we're going to work with it. But for me to talk about motion, I first have to talk about position. So, I mean, position's a pretty obvious idea. It's where something is. That if I say, oh, the position of this object is here, it's just, yeah, it's where the thing is. Like, this is in my, this way. This is in my hand. That's its position. It's the location of something. Now, what you might not always think about is to define the position of any object, you need to have two requirements. And one is you have to have a 0 point. When you say something is 2 meters away, you always say away from a spot. That there's no set absolute reference frame. That we always need to have a zero. That if you're measuring a spot, where you put the end of your tape measure or meter stick or whatever you're using. So whenever you talk about position, you must have your 0 point, but also a direction. If I say that something is 5 meters away from me, that's going to give a circle of possible places it could be that is anywhere within that circle that we don't know exactly what that is. That when you say position, not only do you have a 0 point, but a direction it's in. Is it to the right? Is it to the left? Is it up? Is it down? And because we're on a science course, we're going to always measure our position in meters. Now, as we start getting into equations, we're going to start having symbols. Oop, to me, these things. I got ahead of myself. Sorry, I misspoke. I don't have my one thing over showing what's next, so let me change it to that. There we go. I suck at doing this online. So, most of the time, though, we're talking about motion. We're not really going to care about position of something because we're talking about motion. We have things moving. So instead, we will normally talk about displacement. What I have right here is a right off Google, the path to get from the middle of Oneonta to SUNY Delhi. Actually, possibly from my house. Yep, from my house to SUNY Delhi. And what you can see is that according to this path, it is 21.8 miles. That is the distance I travel driving in. But if you were to draw a straight line, the common phrase is like how the crow flies, but a straight line from where I am now to the school, that only is a 14.5 miles, a direct line, ignoring up and over hills and around corners and through random circles. That idea is what is called displacement. Displacement, which uses the symbol d, anytime you see a lowercase d, that's displacement, is just defined as final minus initial. It is not the path one takes, but just where did you start? Where did you end up? And for the most part, talking about motion, we're going to deal a lot with displacement. That it doesn't matter that I don't take a very direct path to get into work. That's 21.8 miles long. Just that displacement of the 14.5 miles. Now, that means displacement is very different than distance traveled. That if I have this ship go from here to there, straight over, the distance it traveled just be x2 minus x1 from one to the other. And its displacement is just that too. It went from one side to the other. That's the displacement. That it ended at 2, it started at 1. That's the displacement. But if I took that same ship and it does this path, that's the same displacement because of the fact that it might have done a crazy ass path. It's going all over the place on its way, but it started at x2 Sorry, I misspoke. It started at x1, it ended at x2, and so its displacement is still just x2 minus x1. That displacement-wise, there's no difference between when I did this and when I did that. In fact, another weird thing with this is let's say the ship started on x1 again and does this. That's zero displacement because it started and stopped at the same spot. And so it seems weird to be working with displacement because I'm saying, hey, look, nothing happened. And you can look at this and say, hey, something obviously happened here. But mathematically, nothing happened. And so it seemed like displacement is a stupid thing to really want to deal with. That I could say the distance it traveled, that big circle. And see, that's the big thing here. Displacement isn't the same as distance. But the displacement of an object is just going to be final minus initial. But the distance is the total distance it travels. That if I take, oops, double clicked, if I didn't put a ball nearby, if I take a ball or whatever this is and throw it up and catch it, the distance it traveled is going to be however high up it went at times two, because it went up that high, down that high. But its displacement is still zero because of the fact that it started and stopped at the same place. So once again, it seems like displacement should be useless because once again, this says nothing happened there. But the thing is, because of something called vectors, it ends up mathematically, displacement is more important. You see, all numbers we talk about will either be a vector or a scalar. And a vector is a type of number that has both magnitude, aka the size, how big it is, 1 meter, 2 meters, and so on, but also direction, where the direction is going to symbolize which way it went. Did it go this way, this way, this way, that way? And traditionally, you see like a board thing and an arrow over it, but we're going to do one dimensional. One dimensional means just flat lines. It's going to go one way or the other. And in one dimensional, we can just say, is it going in the positive direction or the negative direction? Now, I have no idea if the video can be mirrored here, so you just have to trust my words over what I'm doing. But the standard is to the right is positive, to the left is negative. And also up is positive, down is negative. And so we'll define anything moving to the right or moving up as moving in the positive direction, and anything going to the left or going down as the negative direction. And that gets back to why when I throw this up and down, I have zero displacement, because it has displacement positive and then displacement negative. That it goes up a meter, half a meter, and then down a half a meter. So it has 0.5 minus 0.5, a displacement of zero. The reason that displacement cancels out is because of these signs, because sometimes it is negative. Now, if something's a scalar, scalars have no direction. So if I tell you, we're going to give this lecture for 50 minutes, I'm not doing 50 minutes to the right. I'm not doing 50 minutes up. It's just 50 minutes. Or if I say something weighs like 10 kilograms, that 10 kilograms doesn't have a direction to it. It's just 10 kilograms. And so we don't need to worry about the directions. That a scalar will always be positive, while a vector could be positive or negative. And position and displacement are vectors. That we always need to include the sign. That it's not 5 meters, it's 5 meters that way. Or, it's not 2 feet, it's 2 feet that way. And so on. My left, your right. So I guess that way to you guys. Okay. Now, just saying, oh, something moved isn't really the most fun and interesting parts of all this. Where it gets a little more interesting is, the rate of movement, the idea of speed. Speed is something that, you're kind of familiar with. When you drive your car, you're going so many miles per hour. That's your speed. Right now, though, we're going to talk about what's called the average speed. That the average speed is just the average over a distance. And the average speed when you go is defined as the total distance you traveled over the total time to travel it. It is a scalar quantity, so therefore it is always positive. Um, but the thing about average speed is it's just distance and time. It ignores any variations. If I go back to that map I had earlier, I'll come back to this slide in a second, but this guy, that if I'm doing the Oneonta to Delhi drive, I'm going to be vastly changing my speed at different parts. That I'll be doing a good 60-ish for most of it, and then I'll hit that 30 mph zone and slow down to, say, 30, then speed back up and hit Delhi and slow back down. That my speed is going to vary. But average speed ignores that. That it would just be the total distance I traveled, 20-ish miles, divided by the total time I traveled it, 20-ish minutes. I'm going to be honest, jumping ahead, average speed, not going to be important. Because if you're doing that drive, you don't give a shit how fast you're going on average. You care about how fast you're going the moment you pass that cop in the 30 mph zone. That average speed ignores any variations on that. But, well, I'm going somewhere with this, so I'm covering anyways. Now, unit-wise, average speed is distance over time. So the units of speed will be meters per second, since we will measure distance in meters and time in seconds. But I spent all this while talking about displacement is how we're going to really do. We're not going to do a distance. We're never going to do a distance. We're going to deal with displacement instead. And so if we're going to do a displacement instead, it seems weird that the speed doesn't mention displacement. And the reason why in physics is we would normally use something else to talk about the rate of movement. That in physics, we would normally instead talk about velocity. Velocity is talking about displacement over time. Now, velocity starts with a V. Its unit symbol is a V. Always be represented by a lowercase v. Average velocity, not just the velocity at a moment. Once again, not instantaneous, but average over a whole trip. That's what the AVE there is for average. Is just defined as displacement over time. And so continuing through with my driving to and from Oneonta to Delhi idea, is that it wouldn't be the 20-something miles over the time. It would just be that 14 miles divided by time. Now, once again, this seems like it's giving less information. It's not saying the rate at which I'm moving. It's just saying the rate that I displaced. But the thing is velocity is a vector. And because velocity is a vector, it also must include direction. That it will matter if I'm going 10 meters per second to the right or 10 meters per second to the left. Where traditional to the right would be positive, to the left would be negative. Now, what it's going to do is your direction will always be the same as the direction of displacement, or the direction of velocity, I mean. And so I would be doing this live if we were in class, but let me grab this little video. If I take this cult and make it do this. So it goes up a little bit and then down. Its average speed would be the distance from going up to down, that total distance, which that track is about a meter long, so it'd be about a meter and a half of distance it traveled over that time period. But its displacement would just be the same as if it went from straight from here to there, ignoring how it got there. Just ignoring the path, but just saying from this to this. So I would say it moved about a negative half meter, that it ignores that up bit ahead of time. Now, units, still meters per second. Also, sometimes are often asked for magnitude of displacement. Oh, sorry, magnitude of velocity. I misspoke. If I ever ask for magnitude of velocity, it means I'm ignoring the negative sign. It's just give me the value. So if its value is like -5 meters per second, you would just say 5 meters per second. I don't do that too much in this class. But it is a thing sometimes. I say magnitude, you can drop the negative. Although if you keep the negative there, I normally don't mark it wrong anyways. Good so far? As I said before, if you have questions, unmute, interrupt, and I will keep going. It's so weird to just be talking. Feels like I'm just talking to myself at my computer. Moved on. Now, the thing with this speed and velocity is, let's say I have two cars, a blue one and a red one. and they both go from point P to point Q in the exact same amount of time. Both cars will have the same average velocity because they both have the same displacement, but they will not have the same average speed because the blue car traveled further. It traveled further in the same time. It has a faster speed, which once again really makes it feel like speed should be more useful here. But the thing is, well, there's a few reasons why it's not. One is we're dealing with average. And once again, no one gives a shit how fast you're going on average. It matters how fast you're going at a moment. And two, the reason that the velocities are the same is it's dealing with this size. That for the blue car, it's initially going up, has some piece of it going up, which is positive, and then has some bits going down, which is negative, and then down, which is negative, and then up again, which is positive. That the negatives and positives kind of cancel each other out. And the thing is over average, over the distance, those go away. But if we instead say, okay, screw average, let's do instantaneous. How fast are you going at an exact moment? Like, what is your speedometer say in your car right now? That instantaneous velocity means you're just going to look at really instantaneous velocity is just the average over a really, 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 really small time period. That we are going to take, okay, going to go mathematical for a second, the limit as time approaches zero. But my short thing is instead of saying, let's look at the velocity between here and here, let's look at the velocity between here. And that when we do that, we make that time limit zero, it'll be what the speed is at that exact moment. And what happens is if we make, let me annotate, don't do this often. So if I go from here to there, the average speed and the average velocity are going to be very different because the velocity is just going to be going taking the straight line from one of my little filled in points to the other one, while the speed is going to take that whole distance. But if I look at a very small time period just from there to there, its speed and velocity, distance and displacement will end up being the same if I'm looking at such a tiny time thing. If you're looking at just the tiniest thing, there won't be enough time for it to go crazy and go all around. And so what happens when you do instantaneous is that the average and instantaneous, oh, I'm getting ahead of myself, is that what's going to happen, let me go to the next slide actually, is that the average and instantaneous speed will be the same. But here's the thing, velocity is a vector. Ooh, I'm going to re-say that once again. I think I said the wrong thing. Is that when you get infinite time, the average speed, sorry, the instantaneous speed and the instantaneous velocity will be the same. I think I said the average and the instantaneous would be the same. That is not what I meant. When you get a very, very period of time, the instantaneous speed and the instantaneous velocity will be the same. And so, but the difference is that the velocity, or at least the magnitude will be, because the velocity will have a direction. That if your car is going 80 miles per hour, that's your speed. But if you're going 80 miles per hour north, that's your velocity, which if you're driving down the highway, it matters which direction you're going on. And this is why velocity becomes much more important, because when we have the velocity, once you get not average, and seriously, who cares about how fast you're going on average? Once you get instantaneous, that it's all going to be based off, yeah, which way are you going and how fast you're going. And this is the reason we'll really use velocity, is because it can tell us how fast, which direction, no problem. Keep in mind, speed, always a scalar. Velocity, always a vector. The band, they might be giants, did a song about this. I'm not playing it, but that's a thing if you really want it. All right. At this point, what I would normally do, and this is like throughout the rest of the chapter, this isn't normally as in like because we're stuck online because it's, not snowing right now. But like, but I normally, after I cover a topic, I do an example problem. So I was about to do an example problem. This is our first real physics problem I'm about to do. And so before I do the problem, I want to talk about problem solving in general real fast. Um, our first 4 chapters of this class are going to be what is called mechanics. Uh, Also referred to sometimes as physics one, but that's only the first 4 weeks. We're going to be doing real world situations. And when you're solving such problems, there's steps you should always take. And since I'm about to do a problem, I want to go through those steps and then I'll do a problem about average velocity, average speed. When you get out of mechanics, so chapters 5 through 12 for the class, most of these steps will still hold true, except for one of them, the first one, which is how to solve problems, though, is step one, excuse me, draw the situation. Make a drawing. Doesn't need to be fancy. Make a drawing, it'll make your life easier. And I said that will go away once we hit chapter 5 and move on. But the rest will all be true. See, what physics is applied math. It's not going to be just pure math. You're not going to be just like, oh, this, here's some numbers, do it. But it'll be a real world, or in my case, a pop cultural situation. And so how to solve a problem should be as follows. Take that block of text and collect all your variables. Collect everything given and write it down with those symbol. D equals this. T equals this. V equals this. And include whatever you're solving for. I know this is something equals question mark. So like T equals question mark. After you do that, make sure everything is in SI, meters, kilograms, seconds. And then you play the matching game. The hardest part of physics is knowing which equation to use. But the secret to it is if you write down all of your variables and have them all there, all of the letters that represent the numbers in the equation, how to pick your equation is find the equation with the same symbols. That if you have a D, a T, and you want V, you're going to look for an equation with D, T, and V. And so you could just go through the equations. You would know, or at least the equations from that chapter, because let's be honest, I'm doing one chapter at a time, and figure out which one has the same symbols. That'll allow you to solve. After you solve, always make sure you answer the question. If I said how much time elapses and you tell me 20 kilograms, 20 kilograms isn't a time. It's not going to help you. Make sure your units are correct. If your units work, the problem should be fine. And do make sure it makes sense. If the example I always gave is my first semester teaching, not this class, but physics one. I had a problem where someone had a meter long steel ball and was trying to stretch it. And that problem involves dividing. Let me get back to my little right on here again. Um, Involved taking something and dividing by 20 times 10 to the 10th. And almost every single person in the class instead divided by 20 and then multiplied by 10 to the 10th, which meant they were all off by a factor of 10 to the 20th. And they got that the steel ball being pulled on by a person got 10 to the 20th meters long. And no one thought that it didn't, well, not that made sense. Make sure the answer makes some semblance of sense. Um, I have a video that covers this. I'm not going to play it, but there is a video. There's also an online demo. There's a PowerPoint on just that. Um, but I'm not going to go through it. It's just there if you want it. But let's go back to velocity and let's solve a velocity problem. And here's my problem. Light moves in a vacuum at a constant velocity. This constant velocity is so important, it's its own symbol. Its symbol is C. And C is defined as 3 times 10 to the 8th meters per second. Now, this is a constant velocity, so this would be the same as an average velocity. I'm using a C here, just, I don't know, making my point. How many seconds does it take light from the sun to reach the Earth if the displacement between them is 1.5 times 10 to the 8th kilometers? So I'm going to do that process. Step one, picture. So there's my picture. Sun to the Earth is 1.5 times 10 to the 8th kilometers. And I'll write down what I know. Now this, I say a constant velocity of C. Constant velocity means that's your average velocity, because if something's moving at a constant velocity, the average velocity is the same thing. So my V average is C. I say there's a displacement of 1.5 times 10 to the 8th. But that's in kilometers. That's km. We never work in kilometers. I need to convert that. If it's 1.5 times 10 to the eighth kilometers, I need to convert that to meters. Well, I would need to know the conversion. And once again, I will always give you the conversions as needed. But this one, I'm just going to give it to you now. 1 kilometer is 1,000 meters. And so that displacement, doing a unit conversion, I'll multiply by a ratio to cancel out kilometers to get meters, is 1.5 times 10 to the 11th meters. And so what I know is, there we go, is I know V, I know D, and I ask how long, how many seconds. So I want T. And so this is what I said with the matching game. I need an equation with V average, D, and T. Now, at this point, I've only really done like 2 equations. One of them I didn't use any symbols on. So it's kind of obvious for this case because it's all you got. But if you were going through earlier, you'd say, look through, find an equation with V, D, and T. And my equation with V, D, and T is that V average is displacement over time. Now, I am solving for time. If I want to solve for time, I do need to rearrange this equation. Time is in the denominator, in the bottom of a fraction. And so I'll need to get it out of that. Whenever you rearrange your equation, if you're solving from the denominator, start by getting that into the numerator, the top of the fraction. You see, if I take this equation and multiply both sides by t, I get t up top. What I can do is now divide both sides by v. And if I divide both sides by v, I have t alone now. And what I'll find is my time is the displacement over the velocity, which gives me 500 seconds, which for the record is about 8 minutes, 8 1/3 minutes. So 8 minutes, 20 seconds. Okay. Okay. Now, if we're dealing with instantaneous velocity, that means our velocity is sometimes changing, that our velocity can be shifting. If I go back to, that's not what I wanted to hit. I wanted to hit this. That if I go back to this thing I was showing earlier, that the velocity in here is not constant. On the way up, it had a positive velocity. On the way down, it had a negative velocity. It was shifting around. And so I can start talking about what happens when velocity changes. If your velocity is changing, you have what is called acceleration. Now, velocity is a vector. And so what we can say is we have an acceleration, which is also a vector. And the acceleration vector is by definition delta v over delta t. Delta, for the record, I use this term every once in a while, so I always like to cover it. It's this Greek letter that looks like a triangle. Delta just means change in. Delta, by definition, just means final minus initial. So what average acceleration really is final velocity minus initial velocity over final time minus initial time. Now, traditionally, people, when they're timing things, they start at 0. Right? Your initial time is basically always 0 because you're going to start the stopwatch then. So this is normally just written as final velocity minus initial velocity over time. Units are going to be meters per second squared because it's meters per second divided by seconds. It is a vector. The direction of it matters. And when you see the VF and VI, that just stands for final and initial velocities, respectively. But what we can say is that, yeah, anytime your velocity is changing, you have this acceleration. Now, this. If something is moving at a constant velocity, I don't know why I bother with that. If something is moving at a constant velocity, and here's this guy. Nope, that's what I meant to do. Nope, this. What happens? Okay, on this video that I have open on the bottom, this is an accelerometer. I don't know if you can see my mouse to see what I'm pointing at. Maybe you can see this, maybe you can't. The thing on top of that cult with an A and the blue and green arrow is an accelerometer. It just lights up to show acceleration. If something's moving at a constant velocity, you see like when I push it and when it hits the end, it shows acceleration, but when it's going, it shows a tiny bit, but not much. That's just friction. If something moves at a constant velocity, what's going to happen is it'll have no acceleration because your final velocity is some number. Your initial velocity is the same number. So something minus itself is zero. You will have no acceleration. But if something is speeding up or slowing down, you're going to have acceleration. Now, it's nice to think positive acceleration means go faster, negative acceleration goes slower, but that's not actually true. Going back to this video, you note that the entire time this is on the cult or the track, except when I'm touching it and it hits the end, it has red lights again. That on the way up, the lights are all red. On the way down, the lights are all red. But on the way up, it's slowing down. It's going slower and slower and slower. And on the way down, it's speeding up. It's going faster and faster and faster. If your velocity and acceleration are in the same direction, you're going to go faster. And if they're both positive, you're going to go faster positive. If they're both negative, you're going to go faster negative. It's when they're in opposite directions. If your velocity is up while your acceleration is down, then you're going to go slower. Or if your velocity is down, your acceleration is up, you're going to go slower. So if velocity and acceleration point in the same direction, you're going to go faster in that direction. But if they're opposite, you're going to slow down. What direction depends on what direction you're moving in, but it will mean slowing down. Now, you can have a change in acceleration also. Like if you watch this little video, that it starts with green lights and then goes to red lights when I start it, and it goes from red lights to green lights when I stop it, right? Acceleration is changing. There is a term for change in acceleration or for change in time. It's called a jerk, like you jerk to a stop. We're never going to talk about that though. Um, what we're going to do instead is going to talk about what happens when your acceleration is constant. And if your acceleration is constant and not changing, you no longer have average acceleration. You just have instantaneous acceleration because the acceleration is constant, like it was while I'm not touching this thing. Once again, while I'm touching it, it goes out the window. But when I'm not touching it, the acceleration is constant. Um, what I can say is that, yeah, instead of average acceleration, just A. Now, keep in mind, acceleration is final velocity minus initial velocity over time. If I take that equation and I multiply both sides by t and add the initial to both sides, I get this equation. And this is an incredibly important equation. What this equation says is what your velocity is as a function of time. That if something is moving and you want to know how fast it's going, you just need to know how fast it was initially going and the acceleration in time. And this will always work to do that. Now, keep in mind, acceleration and velocity are vectors, but the vectors kind of work with this equation and can come right out of it. Let me go straight to an example problem. This example problem might be an old exam problem. I can't remember. It might be, it might not be. I don't remember. I've done things like this though. And for this one, I did Fast and Furious. The first one. The first one when shit wasn't as crazy. So, in the first Fast and the Furious movie, Brian is shown driving at 130 miles per hour, which is 58.1 meters per second. You can see that on the bottom left. And he hits some nitrous oxide. That makes him go up to 150 miles per hour, which you can see on the right. Let's say it takes 3 seconds to do that. What is his acceleration? So let's make me a little smaller. Sorry. Okay, no, I didn't skip anything. Okay. So I'm going to make my drawing. Always start with a drawing. And here's my drawing. And what I'll do is I'll start labeling everything. And I'm saying he was initially going at 58.1 meters per second. I did the unit conversion for you. He sped up to 67 meters per second. He did this in 3 seconds. What's the acceleration? Now, at this point, I should check to make sure everything's in SI, but it is. And I'll find the equation. Now, I need an equation with V final, V initial, A and T. And the equation with V final, V initial, A and T, that's this one. And so I'll use this equation to solve. And so what I'll do is I'll kind of make some more space. And I'll solve for A. If I subtract V initial from both sides and divide by time, I get this equation, which honestly, I started with this equation. This was my average acceleration equation. So you probably could have just jumped straight here. I didn't because I always use that V initial plus AT equals V final equation. By nature, that's a very important equation. But if you had jumped straight to this equation, because, let's see, let me jump back a few slides. There it is, right there on this slide. You would have been fine. And at this point, though, I'll just plug in numbers. That my final is 67, my initial is 58.1, my time is 3. And I get 2.97 meters per second squared. All right. That's general idea. For the next little bit, rest of today for sure. So I'm just looking at how far I plan on getting today. I'm going to talk about a special case. See, this equation always works. V final equals V initial plus AT. But let's talk about the special case known as free fall. If something is in the air, right? Not touching it, but it's in the air. It's going to accelerate downward. You drop something, it falls. You throw something up, it slows down, then falls. That anytime something just rolled over my own foot, that hurt. Okay. That anytime something's in the air, it's gonna fall. I mean, it has like wings, or it's a bird or a plane or a Superman going on that, then maybe not. But like, as long as nothing is acting on it, things always fall downwards. That's because on Earth, all things always feel a downward acceleration equal to 9.81 meters per second squared. This number is so important, it gets its own symbol. That symbol is G. That G equals 9.81 meters per second squared. That is the free fall acceleration due to gravity. And anytime something is in the air, that will be its acceleration. Now, traditionally, we define up as positive, and things fall downwards. So what we can say is if something's in the air, the acceleration due to gravity is negative G. This is crucial and really messes with people. Your acceleration is negative 9.81, but G is positive 9.81. Whenever G is in an equation, put it in as positive. The negative sign will show up in other places, but every equation with G equals positive 9.81. Just your acceleration is negative G, but the number G itself is positive. And anything that is in the air and nothing else is acting on it, so no like rocket engine or anything like that, we will say is in free fall and feels this acceleration of negative G. Now, I keep saying anything, and like, who knows if this is going to work in my little tiny, you know what? Let's make my thing bigger for a second. If I just take like a piece of paper and go, it's going to slow down, right? Like that didn't just fall down as fast as this thing. It went noticeably slower. What's happening though is that I said this whenever nothing else is acting on a thing. And when I drop that, something else is. Air resistance. But what would happen if there was no air resistance? The most traditional version of this question was done between a feather and a hammer. This was thought up by Galileo way back in the day, and amusingly first tested on the moon. But we know that in real life, if I drop a feather and a hammer, that the feather's going to when the hammer plummets. But what if there was no air resistance? This video that I'm about to play, which you're hopefully the audio works, but if the audio doesn't work, the audio it doesn't, it's fine. It was done in a NASA space power facility in Sandusky, Ohio. This area is a big room that's a vacuum chamber. It's the world's largest vacuum chamber, where literally they sucked all the air out of this room. And what they did is they set up feathers and a bowling ball and set it up to release them both same time, and then filmed it in slow motion. As I said, in slow motion. What you can see is both of them fall at the exact same rate. That without air resistance, all things fall at a rate g. It doesn't matter if it's a hammer. It doesn't matter if it's a bowling ball. It doesn't matter if it's a feather. It doesn't matter if it's that post-it note I was doing. If you have no air resistance, everything falls at g. Always. The reason sometimes other things might go slower is because of that air resistance. Now, if we were in person, I would do this live in class. We're not, so I guess you have to deal with a second video. But I can just do it with a bowling ball and a metal ball bearing. Sorry, did I say bowling ball? A ping pong ball and a metal ball bearing. That ball bearing is solid metal. And when I drop both, they fall at the exact same weight, even though one weighs a hell of a lot more than the other. Because in free fall, everything falls at G. And the good news is, well, if there's air resistance that would go out the window, we are going to always ignore air resistance throughout the rest of this class. I have a few slides on air resistance coming up that's just kind of like, here's how air resistance works. But yeah, we're just going to say air resistance is 0 when we do these problems. It makes life easier, and there's no reason not to. Now, no air resistance. Let's say we just drop something, right? That we just take a thing like those balls I just had. Do I have? Nope. Sorry, I'm going through my videos. I don't. So I'm just going to like with this thing again. If I just take this and drop it, right? I can talk about the distance it falls. If you drop something, the displacement it falls will go as 1/2 gt squared. Note, this is not if I like throw something upwards like this. It is not if I throw something downwards like this. This is just if you drop it from at rest. If you drop something at rest, that its displacement, how far it falls, goes as 1/2 gt squared. Now, note the displacement should be negative and g should be negative because g is going down, d is going down. Commonly, the negative sign is not put here because it's kind of assumed that if you drop something, it goes down. But what we can find is that it will accelerate as it goes, and it will work out exactly how far it drops. This is an incredibly important equation. It will be on your homework. It will be on your exam. Make sure you have it. You can also figure out the velocity when it drops. Its velocity is a function of time. See, we know v final equals v initial plus at, but we're saying this if something is just dropped. If it's just dropped, its initial velocity is 0. And so that means v final is just negative gt. And what you get if you just drop something, not only can you find the the distance it follows, but its velocity. Now, very common people when trying to find velocity something drop try to use the displacement over time equation. But that's the average. That would be the average over this whole trip. But if you want to find how fast is something going when it hits the bottom, use this equation. And this would be its actual speed when it hits the bottom. Okay. Let's do an example problem. And I'm going to spoil the ending of a movie that, if I'm spoiling for anyone, I apologize, but it's old and a classic and going slightly gruesome. At the very end of Die Hard, the original one, the good one, Hans Gruber falls 128 meters. How long does he spend in the air, and how fast is he going when he reaches the bottom? Here's what we know. I want to solve for a time. And I didn't do it this time. I was bad. So let's just do it with my pen. I know this. That is a distance, a displacement, how far he fell. So I need an equation with d and t in it, which really isn't enough. But once again, he is falling. Falling means gravity, means g. So I need an equation with d, g, and t. And we now know that d equals 1/2 gt squared. Now, sometimes I will give you t and ask for d, which makes this very simple. Sometimes I'll give you d and ask for t, which makes this more complicated. But I can rearrange and solve this. See, if I multiply both sides by 2, I can get rid of my half. If I then divide both sides by g, I can get t squared alone. And if I square root both sides, I can get an equation for the time. The time is the square root of twice the displacement over g, or 2 times 128 over 9.81. Let's do that math. 2 times 128 is 256. 256 divided by 9.81 is about 25-ish. Square root, you get about 5. Now, part B. How fast is he moving when he reaches the bottom? You want to know velocity at the bottom? V equals negative gt. And so it'd just be negative 9.81 times the time. And that will be the velocity. Now, once again, this just assumed, sorry, I just broke the thing I've been throwing around. This just assumes drop. But it can be used for solve problems like this. Nope. Trying to erase. There we go. Okay. What time? 12:48. I'll do what tiny bit more. Where this can go slightly interesting is when something is. Oop, I drew a green line by mistake, I guess. Um, is when something is thrown upwards or downwards. If something is thrown downwards, I'm not going to really worry about the equations. You just have a negative initial velocity. But if something is thrown upwards, and I'm just going to cover up my video there. When something's thrown upwards, at all points in the air, your acceleration is negative g. The acceleration is negative g on the way up. The acceleration is negative g on the way down. The acceleration is at negative g at the highest point. That throughout this entire thing, my acceleration is negative g at all points on that throw. But let's think about these velocities. On the way up, its velocity is positive because it's going up. On the way down, its velocity is negative because it's going down. Now, if your velocity is going to go from positive to negative, it has to pass 0. And when you look at this in slow-mo, at that highest point, right there, there was a moment, split second, where it is not moving. That at the highest point, you have zero velocity. But the thing is the acceleration is always negative g everywhere. But if you ever want to find the highest point when something's thrown in the air, the highest point will be that moment when your velocity is zero. Also, as an interesting thing, at any given height, the magnitude of the velocity is the same. That if I was to draw a straight line, like not very straight, but whatever, and I could say the velocity of the ball right there, I need my line up higher, so I'll just do this. The velocity of the ball right there will have the exact same magnitude of the velocity of the ball right here. That the magnitude would be the same. That if it's 2 meters per second up, at that exact same height, it would be negative 2 meters per second on the way back down. That the magnitude is the same, but the signs will be opposite. And so if I throw something that leaves my hand at 5 meters per second and I catch it at the same height, it hits my hand at negative 5 meters per second. That it all becomes symmetric because the acceleration is constant. All right, I just realized I went a minute over. It is 12:51. I apologize. I am going to stop there. And see you all Wednesday where we're back to doing this in person.